Hello everyone. My apologies, I hit the wrong button, so I have to start recording a second video to continue. So this will be part 2. So we left off talking about the list of strong bases, and then we get to water. And then remember that water is amphoteric. Okay? It can act as an acid and a base. Very weak though. Very weak. Very tiny amount ionizes in water. And we came up with this equation, another equilibrium constant, concentration of H3O times the concentration of OH minus is equal to 1 times 10 to the minus 14. And for neutral water, the hydronium concentration is 10 to the minus 7, and the hydroxide concentration is 10 to the minus 7. Okay, and then in the next slide, basically showing the same thing, that water is amphoteric. It can act as a weak acid or a weak base. And then we go to slide 17, conjugate acids and conjugate bases. The key thing is here is that they differ by an H+. So if you have a question and you're comparing different species, and you can see that they're the same except one has one more H plus or doesn't have an H plus, that they differ by one H plus, that's the right pair. If they have things that are not the same, they can't be a conjugate acid base. So here's our acid. When it gives away the H plus, what is it left with? Just the Cl minus. So this is our acid and this is our conjugate base. How do they differ? By an H. Now here's our base, water. So water receives the H plus because it's a base, and so when it receives the H plus, it becomes a conjugate acid, H3O plus. And notice again they differ by an H plus. Okay, so that's a little trick to help you. Slide 20. So I derive this. You don't need to know the derivation, but you do need to know that Ka times Kb equals 10 to the minus 14. So if you were given a problem where you needed to find a Ka, but you were given Kb, you put in the Kb value and then solve this equation for the Ka. So Ka times Kb is equal to 10 to the minus 14. Okay, and then that brings us to the pH scale, which is slide 21. And I think you all know this. It's 0 to 14, and I told you they came up this scale just so you could use the positive exponents and not have to do 10 to the negative 1, 10 to the negative 2, or 10 to the minus 14. So we just use the positive numbers, 0 to 14. So 0 to 7 is neutral. Closer to 0, it's a stronger acid. 7 to 14 is a base. Closer to 14 is a stronger base. And 7 is neutral. And here we can see the difference in hydronium and hydroxide concentrations in each of these situations. You don't need to know the specific pHs. That was just for illustrative purposes. Okay. Then we go to a beautiful equation. All equations are beautiful, but this is a beautiful one. And this was the shortcut that chemists came up with because we're lazy. So we don't have to use negative exponents all the time. We just say the negative log of the concentration of H plus or H3O plus. Remember, these two are interchangeable. They're interchangeable. They both mean the same thing. Sometimes, this just shows it without the water. But anyway, it's a negative log of the hydrogen ion or hydronium ion concentration. That's how we find the pH. And then we go to slide 27. Remember that whoops, wait a second. Slide 27. Oh yeah, okay. So here, this is how we find the pH, and then pOH is the negative log of the OH concentration. So pOH, negative log. And later we get into the pKa, which is just the negative log of the Ka. pKb, the negative log of the Kb. pKw, the negative log of the Kw. Whatever's, when you have P of something, it's whatever comes after that. It's a negative log of that. So P of me is a negative log of me. Alrighty, let's go to slide 32. And remember that pH plus POH is 14. So in some problems you have to find the POH first because the OH concentration is given, and then once you get that, then you can find what the pH is subtracted from 14. Alrighty. Then another beautiful equation. Oh, I'm sorry, wait a second. This is the pH, let's see, 33. Yeah. So this is just reviewing what we did for a strong acid or a strong base. For a strong acid, the pH is the negative log of the concentration of the H+. And for a strong base, the pH is the POH is the negative log of the concentration of the OH-. And remember that pH plus POH equals 14. So if you're starting with a base and you want to know the pH, first you have to get the POH, and then you use this equation. Okay, then we go to slide 40. Okay, slide 40, what I have highlighted here is the shortcut formula. This is going to be on the reference page of the exam. For a weak acid, you need two steps to find the pH. First, we use this equation, the square root of the K sub A times the concentration of the weak acid, the initial concentration of the weak acid. Once you get the H3O plus, then we do pH as negative log of H3O. So that is slide 40. So this is a summary for acids. To find the pH of a strong acid, it's a negative log of the concentration of the strong acid. One step. For a weak acid, it's going to be, first of all, you find the hydronium concentration through this equation, and then once you have that, then you use the pH as a negative log of the hydronium concentration. Again, that's slide 41. And now we go to the beautiful equation for a weak acid and for a weak base. I should say the beautiful equation for a weak base. We've already done the weak acid. So the weak base, I derived it using the ICE table. You don't have to use the ICE table, and this will be on both of these equations will be on the reference page in your exam. You just have to remember that's for a weak base. The square root of the K sub B times the concentration of the weak base, the initial concentration. And as we just said, for a weak acid, the hydronium concentration is equal to square root of the K sub A times the initial concentration of the weak acid. So these are for a weak base or weak acid. That's how you get the hydronium and hydroxide concentration. Okay, now we move to slide 51. Excuse me. And this is a very good review slide. I gave you a hard copy of this, so you should know the strong acids: HCl, HBr, HI, nitric acid, sulfuric acid, perchloric acid. These are the strong bases. Okay, we went over the KW formula, and you should know all the equations, have them memorized. However, I will give you the formula on the reference page for the weak acid and for the weak base. Notice for a weak base you got to go through 3 steps to get to pH. For the weak acid you have to go through 2 steps. For the strong acid you only go through 1 step, but for the strong base you have to go through 2 steps to get to pH. Okay, we move to slide 55. Again, it's repeating what I just said. So you need to memorize the strong bases and the strong acids. Okay, and then in slide 56 and in slide 57, you should go over those, and you should know how to determine when you mix these salts with water, will the resulting solution be acidic or basic or neutral? So I give some examples there in 56 and 57, and then 58. What happens when you have two weaklings together? They're both weak. In other words, you have a weak acid and a weak base. Well, you got to compare their K's. Whichever K is bigger, that'll be the one that wins out. So in this particular case, when I add this salt to water, I form a weak base and a weak acid, but the the Ka is bigger, and so the resulting solution will be acidic. And then in slide 59, I'm just reviewing the comparing the Ka's and Kb's in that situation when you have two weaklings as your products. If the Ka is bigger than Kb, it'll be acidic. If the Kb is bigger, it'll be basic. And if they're equal to each other, then it's going to be neutral. And here on this slide, this is slide 62, I give you some more practice, and I give you the right answer. I circled the right answer, whether it's basic, acidic, or neutral. So you should be able to handle this. And remember, one of the tricks is, the question will be, what happens when I add this to water, or any of these salts to water? Remember, the little trick we did was we wrote water as HOH, and then we just did a double replacement. The partners, we have an exchange of partners, and then looking at the products, you have to figure out which one is a strong base or a weak base, or a strong acid or weak acid. In this case, for example, it's strong base, weak acid, so the strong base wins out. How do I know that's a weak acid? Because it's not on the list of strong acids. So there will be questions like that. Actually, I think 3, where I add different salts to water, and then I ask you, will the resulting solution be acidic, basic, or neutral? If you understand it, it should be fairly easy. And then let's see here, let's go to the recap. Here's our recap of these things. If the resulting, after you add the salt, if the resulting is a weak base and a strong acid, it'll be acidic. If it's a strong base and a weak acid, it's basic. If it's a strong base and a strong acid, neutral. And if it's two weaklings, it depends which K is bigger. And again, you have to recognize whether it's a weak base or a strong acid. You know it's a weak base because it's not on the list of the strong bases. Or you know it's a weak acid because it's not on the list of the strong acids. So you need to memorize those few strong bases and strong acids. And then we mentioned something about polyprotic. This will be on the exam. One of the definitions you should know. It's basically an acid that can furnish more than one proton, okay? So like H3PO4, it can shed one proton, and then it can shed a second proton and shed a third proton. So you should know that definition. It has the ability to furnish more than one proton, so it's polyprotic, which many protons. Okay. And this is the last slide for this chapter. And basically it just repeats the same thing again, that these are the strong acids, and if it's not one of these, then it's a weak acid. And if it's a weak acid, it brings an equilibrium, and the Ka is very small, like 10 to the minus 10, 6. It has a 10 to the negative exponent. It's weak. The Ka is small, but it involves equilibrium. These again are the strong bases you have to memorize, and if it's not one of these, it's a weak base. And if it's a weak base, then that involves equilibrium. And again, the K, the equilibrium constant for the base, will be small. So again, make sure you know all the terms. There will be matching. There will be 10 matching questions on the exam. So make sure you know all the terms. I want you to get all those right. And it's a shame when people didn't study the terms and then they get a lot of points off on the first page, because it's meant to be the easy page. And now we're going to move to chapter 15. Let's see if I can find it. So now we're going to move to chapter 15. Okay, chapter 15, slide 1. You should know what a buffer solution is. It resists changes in pH. It's very helpful, very important in the functioning of the human body and all living organisms. It's a buffer that helps keep our blood at the proper pH in the human body. Titration is a way to determine the concentration of a substance in a given sample, and of course, since we're studying acids and bases, that's what we titrated, the acids and bases. Okay. Next slide. How do you form a buffer? It's a solution consistent of a weak acid plus its conjugate base, or a weak base and its conjugate acid. Remember, the conjugates differ by an H+. Another way to talk about a buffer solution, you could say, and this is what Active Chem does, a buffer solution forms when a conjugate weak acid, weak base pair are mixed together. Same thing. Both of these are the same, just expressed a little differently. And I can't emphasize enough, this is about the third or fourth time I've said it, they differ by an H+. So if this was an acid, after it gives away a proton, it's left with this, the base. So you know that this is the pair. This is the acid, this is the base, they differ by the H+. And the H+, of course, is given to the other reactant. Okay. And then we go to our Henderson-Hasselbalch equation. Of course, you should look at all the slides. I'm just highlighting. And we've calculated the pH of a strong acid and a strong base, and the weak acid and the weak base. And now we learn how to do the pH of a buffer solution. And again, all these equations are always true. Reflect what's happening in nature. And so this will also be on your reference page, but you have to know that this refers to the pH of a buffer solution. And remember that pKa is the negative log of Ka. So pKa plus the log of the base over the acid. The way I'm going to have it for you on the reference page is like this. You have to know that A minus is the base because it's missing the proton, and HA is the acid. It has the proton, and it's going to give it away. So that's our equation to find the pH of a buffer solution. Okay. Let's see, that's 9 and 10. I want to go to slide 12 and 13. So this is an example that you can look through. In this case, we weren't given the pKa, so we had to find, we're given the Ka, then we have to find the negative log of it to get the pKa. And then we go ahead and substitute it in the equation. You can look that over. Here's another example that you can look over. It's 12 and 13. Now I want to go to slide 16. Again, I'm highlighting. You should look through all the slides. You should know that the buffer capacity tells you how much acid or base you can absorb. Okay? So that you may find that in the matching question. Make sure you know that. Okay, slide 19. Endpoint. Endpoint occurs when the indicator changes color. So endpoint is equal to the point in the titration where the indicator changes color. So let's say you have an acid, it's clear, let's say this is phenolphthalein, it's colorless. As you add the base at a certain point, it's going to change color, and when it changes color, that's called the endpoint. So endpoint is the point where the indicator changes colors. Again, for the matching, you may see that, so make sure you're clear on that. And again, going through review of a few things. How to find the pH of a strong acid and a strong base. How to find the pH of a weak acid and a weak base. And then the Henderson-Hasselbalch to find the pH of a buffer. Okay. Remember, the top part of the equation, A minus, is the base, and the bottom part is the acid. It's a weak acid and a conjugate base. pKa is negative log of Ka, and the concentration of H3O times the concentration of OH minus is 1 times 10 to the minus 14, and we can also say that it's equal to the equilibrium constant for water, and we call that K sub W. Then we get into graphing. So this is the graph, slide 25, the graph of a strong acid with a strong base. Now, if you're given a graph like this and asked to identify it, well, first of all, before you add any base, what's the pH? It's about 1. So you know it's a strong acid. All right? The other thing you notice is that the pH is 7. So when you titrate a strong acid and a strong base, the pH at the equivalence point is 7. And what's the equivalence point? Number of moles of base equals number of moles of acid. And again, you might see that in a matching question. Equivalence point, number of moles of base equals number of moles of acid. And when that's true for a strong acid and a strong base, you're neutralized, and the pH is 7. On the other hand, what happens? What happens when I graph a strong base with a weak acid? So now the curve looks like this. Now, one of the ways you can recognize this, look where the pH is before you add any base. Okay, so it's definitely a weak acid. And then it sort of flattens here. And notice something. In the buffer region, when you're at the equivalence point, the pH is going to equal to the pKa. That's important. The pH equals pKa. And the equivalence point over here, the pH is greater than 7. Yeah. All right. Let's look. So again, if I were to show you this, and I said, what does that represent the titration of? Well, equivalence point is 7, and you're starting with a strong acid. You know that it's a strong acid with a strong base. It has that type of a shape. So there's two clues. One, the starting point of the acid, you can clearly see it's a strong acid, and the equivalence point when the moles acid equals base is neutral. Whereas, if you have a curve that looks like this, what are the clues? Well, first of all, pH is almost 3, so it's a weaker acid. And in the buffer region, the pH is equal to the pKa. You should know that. The pH is equal to pKa in the buffer region. So what is it here? It's about a little bit above, I guess about 5, you could say. It depends. A little bit above 4, maybe whatever, 4.8, around 5, whatever. And what is the pH at the equivalence? It's greater than 7. See that? So that tells you that it's a strong base with a weak acid. So you should be able to recognize this and this and tell the difference. Looking at those clues. All right, so that was 29 and 28. And now we go through the titration. So you should go through the titrations. I'm just going to highlight a couple things. Don't want to hold you too much longer. So now we're talking about a strong acid titrated with a strong base. Okay? Before you add any base, you only have the strong acid. So you're in strong acid land, and you just use negative log of the starting concentration, whatever the starting concentration is here. Strong acid land. Okay, then we're still in strong acid land. I know there's a lot of stuff on this slide. You should look through it carefully, but here we add 10 milliliters of NaOH, and what we do is we calculate by taking the molarity times the volume, but the volume has to be in liters, so you convert the volume to liters, and you get the moles of acid and moles of base, and we see we still have some acid left over, but we have a new total volume because molarity is moles per liter of solution. So we have to take the moles of acid by the total volume in liters, and we get the molarity and then negative log of that, and we get the pH. So we're still in strong acid land after 10 milliliters. And then when we get to 20 milliliters, 12 milliliters of base, we're in neutral land. We've neutralized. So if we look at molarity times the volume of each, we see that they both come out to be 0.06 moles. And remember, the volume has to be converted from milliliters to liters because molarity is moles per liter. We want liters to cancel. So we have 0 moles. We're at the equivalence point. The concentration of acid equals the concentration of the base. That means that the hydronium is equal to the hydroxide concentration. When does that occur? Well, if these are both equal to each other and the product is 10 to the minus 14, then each of them has to be 1 times 10 to the minus 7. And what's the pH of 1 times 10 to the minus 7? It's just 7, neutral. So in neutral land, pH is 7. And then finally, after neutralization point, we keep adding base. Now we've added 40 milliliters and we go through the same process. And the moles of acid will be the same, but the moles of base now will be bigger. And so we subtract them and get 0.014 moles of base. However, there's a new volume now, because now we have 40 plus 20. We have 60 milliliters is the new volume. So we have to convert that to liters, and that's what we do. So we take the number of moles of base divided by that, and we get this. Now remember, because we're dealing with hydroxide, we have to get the pOH first, which we do, and then subtract it from 14, and we get the pH. All right. Let's see, it's slide 42. And so our summary, here, this was our summary slide. And so you should be able to know how to calculate the pH in each of these phases. So we go from strong acid land to neutral land to strong base land. All right. Alrighty, now we went to the titration. This is slide 45 of a strong base with a weak acid. All right, this gets a little bit more tricky because in a weak acid we're involving equilibrium. We're in an equilibrium situation. However, since we haven't added any base yet, whatever the concentration of the weak acid is, we can use that. So we just use this formula. Now, they were mean in this question and they gave you the pKa instead of the Ka. So we had to convert following these steps to get the Ka. And once you get the Ka, then you just use this equation. You get the hydronium ion concentration, and then the negative log of that, and we get the pH. And notice it is a weak acid, so the pH is higher. Okay, so in the first step we're in weak acid land, so we have to use that equation. There's no base added yet. Now, one of your homework problems dealt with this slide 46. This is the most complicated of all the titration steps we've looked at. We're in buffer land. We're in buffer land. Now we've added 10 milliliters of strong base. So what we do is, as we did before, we calculate the moles acid and the moles base. But then we have to go to a weak acid equilibrium situation here. And we're starting with 0.006 of that and 0.005 of that. Well, that 0.005 neutralizes, so we subtract that from each. So we end up with 0.001 moles of acid. And then if you look on this side of the equation, we start off, before the reaction starts, we have 0. But since it's a 1 to 1 to 1 ratio, for every amount of this that is used up, that amount is formed. So we're forming 0.005. So we formed that much of our conjugate base. This is our weak acid. So we go to our Henderson-Hasselbalch equation. We already know what the pKa is. Well, it's given. The pKa is given. And we take the base over the acid. And since the volumes are the same, we don't have to worry about that. We just can use the moles of each and follow the Henderson-Hasselbalch equation and get the pH of 5.44. So we're in buffer land there. And so that's why we had to use the Henderson-Hasselbalch. Why are we in bufferland? Because we have a weak acid and its conjugate base. Because we have that much left over after it's neutralized, and that much of the weak base is formed. So that was the most complicated one. And then in the next slide we go back to, we're going to go to weak base land. Now what happened here? Well, we're at the equivalence point. And notice again, when it's a weak acid and a strong base, the pH is not 7. It's greater than 7. And if it's greater than 7, we're in weak base land. A little bit over 7, 8, or 9, that's weak base. Strong base would be 14. So what do we do here? Well, we found the moles of each, but since we have a weak acid, we set up this equation. We're starting with 0.006, 0.006, so that gets used up to 0, that gets used up to 0, they neutralize each other, but we formed 0.006 moles of this weak base. Well, how do we find the pH of a weak base? Well, we have to first of all get the concentration, moles per liter. We have a new volume here, so we're going to take 0.006 moles by the total volume. The new volume is going to be 20 milliliters plus 12, 32, but we have to convert it to liters. And so that's what we did in this slide here. So we take 0.006 divided by the new volume. We get the concentration of the weak base. Oh, so now we have to use this equation to get the hydroxide because it's a weak base. You've got to use this equation. Okay, now we're not given the Kb. We're given the the Ka, or at least we computed it a couple slides over. We computed the Ka. So if the Ka is that, well, Ka times Kb is 10 to the minus 14. So to solve for Kb, we take 10 to the minus 14 divided by that, and then we get the Kb. Okay, so we use this equation here. We get the POH. Excuse me, we get the OH. Now we want to end up getting pH, but we have to get the POH first because we have the OH. So we take the POH as negative log of that, and then once we get the POH, we subtract it from 14. Okay, so that would be our last step, and then, oh, wait a second, that's not our last step. That was the equivalence point. So it's a weak base. Notice the pH is 9, it's greater than 7. So it's the equivalence point, but it's not 7 because it's a weak acid with a strong base. And the last step was when we overpower the acid and we're only left with hydroxides. So again, we compute how many moles of each we have. Now we're adding 40 milliliters of NaOH. So we have 0.3 times 0.02, we get that number of moles. Now we have more moles of the base, which is the hydroxide. Subtract that and we get this number of moles of hydroxide. But volume is now 20 plus 40, which is 60 milliliters, and we have to convert that to liters. So we take 0.0014 divided by the new volume, and we get, this is a hydroxide ion concentration. And then we find the POH of that, negative log of that concentration. We get the POH is 0.63. We subtract it from 14, and we get 13.4. Now we're clearly in strong base land, are we not? It's very close to 14, 13.4. So that's a recap of what we did and the equations that we used. In the first step, we were in weak acid land, so we had to use that equation. Then we were in buffer land, so we had to use that equation. Then weak base land, we had to use that equation. And then strong base land, we used that equation. So we actually used 4 different equations for each of the steps. And again, at the equivalence point, we're in weak base land. We're not at 7. We're not at 7. Okay, and I think that may be the last. Let's see what else I have. Oh, no, I do have a couple more things. So let's go to 52. We're almost done here. So again, I'm showing this review slide. Okay, repetition is good. The more you see it, the more it sticks. Okay, so these are all the different things we've talked about. pH for a strong acid or strong base, pH for a weak acid or weak base, and pH for a buffer. pKa is negative log of Ka. Ka times Kb is 10 to the minus 14. Concentration of H plus times OH minus is 10 to the minus 14. And pH plus POH will be 14. And as I said, these are equations you need to know. However, let's see here. I'm going to give you these equations on the reference. So this is the first page of the exam, and that's for the weak acid, and that's for the weak base. And that's our Henderson-Hasselbalch. Again, you should know all the terms that are used. And one other thing I want to emphasize here, because there will be a question on this, and you should be able to solve it. Remember I said this thing of when all else fails, think. You know a lot of different relationship and equations. And so you have to think about it to maybe to figure out some of the questions. So you can do it. And as I say, one thing you might do is come back to it later when you're more calm, when you've finished most of the exam, all the easy questions, then come back to the more challenging one, and you might be surprised you're going to be able to solve it. If you have a question involving Ka and pKa and comparing them, here's something I want to emphasize. The bigger the Ka, the stronger the acid. All right? However, the bigger the pKa, the weaker the acid. Now let's see why that's true. So a bigger pKa means a weaker acid. Now let's see why that's true. What's pKa? It's negative log of Ka. P of anything is the negative log of that. Let's say that Ka, this is fairly weak, a very weak acid. 1 times 10 to the minus 10. Well, if you take the pKa of that, it's just going to be 10. Since it's 1, it's basically just the exponent, the negative log of 10 to the minus 10 is 10. So pKa is 10. But that's a weaker acid. What happens when you have a stronger acid? Here you have a Ka 10 to the minus 5 is a bigger number than 10 to the minus 10. You take the log, negative log of that, you get 5. Okay? So, when the pKa is bigger, it's a weaker acid. So they're opposites to each other. When Ka is bigger, pKa is smaller. And here's the point. The smaller the pKa, the stronger the acid, and vice versa. The bigger the Ka, the stronger the acid. The bigger the pKa, the weaker the acid. So you have to think through those. And it should make sense. And if it doesn't, just give yourself a couple of examples. What if I had a Ka of 10 to the minus 20? Well, the pKa would be 20. That's very weak. What if I had 1 times 10 to the minus 2? Well, then the pKa would be 2. So when the Ka is bigger for a stronger acid, the pKa is smaller. All right? So again, when all else fails, think. And let's see. I think that's pretty much what I wanted to tell you. All right. So, as always, I'm available for any questions. I can meet with you in person to also do a review session. I want to wish each of you good luck. And unfortunately, I made a mistake, and so this got broken up into 2 videos. So, without further ado, this is Professor Coppola signing off from the nation's capital.